Hey everyone, I'm Dr. Elizabeth Burakowski. I'm a research assistant professor at the University of New Hampshire, and I'm also a member of the Protect Our Winters Science Alliance. So I'm here today to give you an idea of what's going on with climate change. So that said, welcome to Climate Science 101 with me, your host, Dr. Elizabeth Burakowski. I guess we'll start at the beginning, and I'll tell you a little bit about myself. My name is Elizabeth Burakowski, and I remember my first interaction with snow when I was about 3 or 4 years old in Wisconsin. This is where I grew up with my sister before moving to New Hampshire. This photo was taken probably about a year or two before we moved. You can tell which one is me because I'm in the blue. I have dimples, and my twin sister does not. And shortly after we moved from Wisconsin to New Hampshire, one thing that really struck me was just how beautiful the mountains were up there. We clearly lacked those in Wisconsin, and for us to see that in New Hampshire was just such a wonderful thing. And I also remember our very first memories of learning how to ski. Specifically, we learned to ski at Suicide 6. This is one of the longest lift-served mountains in the United States. So it not only holds a special place in my heart in terms of my very first mountain, but it's also a staple and part of the U.S. ski history. It opened in the 1930s. Its first rope tow was attached to a Model T engine and hauled people up the mountain, and still does to this day. It's right now probably one of my favorite resorts, even though I haven't been there in quite some time. In fact, the last time I was there was not for skiing, but instead it was for a half marathon. Other mountains in the region that had an impact on me, McIntyre, this is where my first ski club was. This one, not many people have heard of, and not many people even in New Hampshire know that our Queen City, Manchester, has a ski resort in it. This one is one of the reasons that I actually became a lifelong skier. When I switched over to snowboarding, that was at Pat's Peak. This is one of our favorite family-owned ski resorts in the region. And last time I was here was actually to see my friends get married. This was about 10 years ago. We still drive by it every day anytime we go up there to their house. And it's still today one of our really exciting mountains that we really want to bring our kids to learn how to ski when they're old enough as well. Now, while those resorts remain open, unfortunately, there's been 600 other ski areas across the region that have not been so lucky. And they've closed for one reason or another, and a warming climate certainly contributes. If you didn't invest in snowmaking in the 1970s, and if you weren't able to compete with larger mountains in the area, you tended to shut down. Some of these shutdowns actually happened more recently. The New England Lost Ski Areas Project tracks resort closures across the United States, including New England, and this one here is Maple Valley in southern Vermont. It closed in the year 2000 and only recently was sold, and the developers look like they're actually going to open it as a brewery as opposed to a ski resort. So unfortunately, it looks like its skiing days are over. When I like to talk about climate change, I like to start really big and then zoom our way in. So let's start with the big picture here. This is a map that's showing the global temperature departure from average. Okay, so we also call these temperature anomalies. Don't think of it as something like that's strange or unusual, but rather something that's a departure from normal. So anywhere you're seeing a blue color on this map, that means that that region is cooler than average. You can see the little color bars up here in the corner, right? So anywhere from 2 to +2, okay? Anywhere you're seeing yellows and reds, that means it's warmer than average. So I'm going to play this movie, and you're going to see the temperature blobs kind of move around, and I'll explain what's going on as it happens. So let's hit play. You'll note in the 1800s and the early 1900s, much of the world is blue. This means it was cooler than average. When we start getting into the 1930s, however, you're going to see the United States light up in red, just like it did there. That was the Dust Bowl. In the 1960s, the eastern US lights up in blue because of air pollution. As we get into the later part of the 20th century and into the 2000s, a really distinct pattern starts to emerge. Notably, much of the northern latitudes, the Arctic, start getting a lot warmer. This is on the order of 2 degrees warmer. And you also note this conspicuous blue hole here. This is indicative of our Gulf Stream slowing down and reducing northward heat transport from the tropics into the North Atlantic. So you might have seen that movie, The Day After Tomorrow. This is kind of what they were alluding to, but it's not quite as severe as what the movie depicted. But it is still an important feature of climate change. When we think of what's going on with the Arctic, it's important to look at sea ice. So this is going to be a similar sort of movie. It's just going to be focusing on the Arctic. Note that this does not go back to the 1880s. Instead, it starts in the late 70s. This is when we had satellites that are able to start tracking sea ice extent in the northern part of our globe. So let's play this one, and you'll see some patterns emerge here. Starting in 1979, you can see that much of the Arctic Ocean basin is covered with ice. And this is at its minimum. So the minimum typically happens in September. That's when sea ice has retreated due to summer warmth and then starts to grow again into the fall. As we get into the late 90s, it starts to shrink. And then I recall when I was in graduate school in 2007, we had reached a minimum right around there. And that minimum keeps getting smaller and smaller. You'll note that this brightly colored sea ice is also very important because it's reflecting the sun's energy. When you don't have that bright sea ice, especially in the summer months, that means that more heat from the sun gets absorbed into the ocean because the ocean is darker. This plays an important role with seeing that previous warming trend that we saw in the global temperature map in the previous movie. What are the impacts of this warming? Well, it's not just sea ice and it's not just warmer winters. We also see impacts on coral reefs very far from our ski resorts. This was in starting in 2014. America Samoa Reef, shown here on the left, is quite healthy. Once we had some really warm temperatures, the reef started dying in 2015, and by 2015, in August, it was dead. And this is a kind of a 1-2 punch. It's not just sea surface temperature, but we also have an impact of carbon dioxide from our atmosphere getting absorbed by the ocean and becoming more acidic. And this also eats away at coral reefs. Climate change has also had other impacts on stuff like fire or increased wildfire. This is from our National Climate Assessment. I'll move myself over here so I'm not blocking that. Which was published in 2018. If you haven't seen the highlights, I highly recommend checking it out. Just Google National Climate Assessment and you can get a pretty good overview of at least what's happening in the United States. And what we can see here with the yellow area, this is what wildfire cumulative forest area burned, so showing how much was burned, would have been without climate change. With climate change, however, it is much higher, right? When we think about what's causing climate change, you might hear some folks say, oh, is this natural? And that's true. Some parts of climate change are natural. So let's go through a couple of these and we'll take a look at what has happened in the past to cause changes in climate. Okay, so to take a look at what's really warming the world, we're going to go through this beautiful Bloomberg illustration that they've put together as a graphical demonstration of real data. This is data from the NASA Goddard Institute for Space Studies. So we're starting here with a temperature graph of global temperatures from 1880 to 2014. You can think of this as the graphical version of that beautiful map that I showed you of the world warming. So instead of seeing blue and orange blobs, we're just looking at a line graph. Anything that's below this horizontal line means that the world, on average, was cooler than average. Anything that's above that line means it's warmer than average. So looking through here, you can see there were periods during the early part of the 19th century, late part of the 19th century, early part of the 20th century, when things were cooler than average. And since then, this is when we've seen a lot of warming. So let's go through some of the natural causes of climate change. So we can scroll down and we'll see, is it Earth's orbit? Earth wobbles on its axis. So that means it's not always directly the same distance from the sun. The axis also changes. So sometimes it's tilted closer to the sun. Sometimes it's tilted not so close to the sun. And then also the timing of the seasons changes. This happens over tens of thousands to hundreds of thousands of years. And what we can see is over this period of time when we've been recording Earth's temperature, it really doesn't have a big impact. When we look at changes in ice ages, however, and I'll get to that later in the presentation, we do see impacts on orbital changes. But over the period of which global warming has been happening, really not a big contributor here. What else could it be? Oh, sorry, I should explain this. So the gray line is the same. This blue line is showing how much of an impact orbital changes had. So you can see not very much at all. What about the sun? You might have heard some people say, well, the sun has an impact on climate change. And this is a little bit true. We do see variations in how much energy is coming out of the sun on about an 11-year cycle or so. They call that a solar cycle. However, when you look at how much of a contribution that has to global temperatures, when you isolate it, it really doesn't have that big of an impact. There are some years, like in 1956, where it might have had a bit more of an impact than other years, but overall, it cannot explain this warming trend that we see in the observed temperatures. What about volcanoes? Volcanoes put out a lot of CO2, don't they? Actually quite a bit, but human industry itself puts out 100 times more carbon dioxide than volcanic activity. And in fact, volcanoes actually do a bit more to cool the atmosphere, especially when they're very large eruptions that put a lot of sulfate chemicals into the atmosphere and block the sun from reaching Earth's surface. You can see a couple of very large eruptions happening in Earth's recent past, but overall, again, these are not explaining this warming trend that we're seeing here. Can we combine those three things and see any sort of contribution to climate change in terms of this warming trend since the 1970s? Really, not much at all. In fact, we would have seen temperatures that would have been cooler, again, mostly because of volcanic activity. So let's take a look at some of the human-caused contributors to climate change. What about deforestation? Well, it turns out deforestation actually might have cooled Earth's climate a little bit. That's because forests tend to be darker, and when we cut them down to make way for agriculture or for stuff like pastures, then we actually see a lighter colored surface of the Earth, kind of like the sea ice effect, and this actually has a slight cooling effect over time. So the contribution relative to how much CO2 gets emitted and compared to how much the Earth's surface cools because it's just lighter in color is actually a little bit, it actually ends up being cooler, not warmer. What about ozone pollution? You might have heard of ozone as being something that we need, and that's true. A good way to think about this, up high, ozone up high is good, but down low, it's no good. So when we see ozone, ozone is actually a greenhouse gas. So when it's down low, it can be damaging to human health, but up high, it's blocking UV. When we see down here how much it contributed, it's really not a huge factor. There is a slight warming, right? That light blue line is above our gray line, right? So it's slightly above average, but it really doesn't explain this huge warming trend that we're seeing. What about aerosol pollution? I had alluded to this a little bit when we saw that cooling on the eastern United States in the previous video that showed the globe. Turns out, well, a lot of these pollutants, such as sulfate aerosols that are from coal burning, don't really cause a lot of warming. Instead, they block the sun and they cause cooling. They also, unfortunately, cause acid rain. So we don't really want to use this as a strategy to cool Earth's climate, even though it is a little bit effective. Instead, the main culprit that can explain this rapid warming trend is greenhouse gases, and namely carbon dioxide. Carbon dioxide is a greenhouse gas that traps heat. When that heat gets trapped on Earth, it raises global temperatures. When we combine all of these human causes and line them up right there, we can see that human factors pretty well explain this observed temperature trend. We can also combine them with the natural factors, and now we can see even these dips in cooling around the 1990s and so, that really explain this observed trend. So you need to put all of them together to reconstruct what we see in Earth's temperature records and understand how our climate is changing and what we can do about it. Ultimately, what this means is that we do need to reduce greenhouse gas emissions because they're trapping heat on Earth. All right, so let's get back to a little bit more about how we know greenhouse gases are warming the world. This is just from 1880 to 2014. If you were to extend this to 2020, you would see the same patterns emerging. But what about hundreds of thousands of years ago? I talked a little bit about that. And it turns out, when we're looking at ice cores, we can start to really see the CO2 and climate connection. In ice cores, essentially what it is just a bunch of snow that's been layered upon layered upon layered, doesn't melt in summer, and forms ice as it gets compacted. When it compacts, it traps ancient bubbles of air that include CO2, carbon dioxide, getting trapped. Scientists can then drill the ice cores from ice sheets or glaciers, analyze the gases that are trapped in the bubbles, and unravel this mystery of what has changed with CO2 and temperature over time. When we look at this from Antarctica, this is for the past 800,000 years, we can see how carbon dioxide as a greenhouse gas that traps heat has an impact on temperature. Right here, we're looking at the blue line, which is the carbon dioxide, and this is on the left-hand axis. So the vertical axis is the one that goes up and down on the left-hand side. You can see it ranging from 175 to 400. And what this means is that is the carbon dioxide concentration in what they call parts per million. So if we were to have 1,000,000 parts of air, 400 of those parts would be carbon dioxide. The other parts would be nitrogen, which is the most common, oxygen, carbon monoxide, nitrous oxide, a couple other gases mixed in there as well. But most of the gases that we're interested in, these greenhouse gases, would be carbon dioxide. So over the past 800,000 years, what we can see is that the carbon dioxide levels, at least in this ice core, never really went well above anything even close to 300. Today, however, we're up above 400 parts per million. When we look at red, that's our temperature. So now look at, we're on the the left-hand side of the graph. Now you're looking at temperature over here, and you can see anything below this 0 value means that it was colder. So this would be an ice age down here, and here, and here, and over there, and going back in time. What do we notice? Well, anytime CO2 goes up, the temperature also goes up. Anytime CO2 goes down, the temperature also goes down. And it's happening roughly every 100,000 years. This is the change in Earth's orbit that is leading to ice ages and also coming out of ice ages. What's changed now, however, is that this CO2 level is now much higher than we've ever seen in Earth's past, at least for the last 800,000 years, and even to the last 3 million years. This means that we are going to be seeing this temperature start to rise dramatically, and we already have seen that. So what do we see like in observations? Remember, those were from ancient bubbles trapped in ice. Well, we can also measure it on Earth's history. This is the atmospheric CO2 using instruments at the Mauna Loa Observatory. So this is far removed from a lot of pollution sources, and it's also what they call in the free troposphere. So it's up in the atmosphere where places that are generally free of pollution, and you can get a pretty good idea of what CO2 levels are. So when I started, let's put this into context with my life history. When I started skiing at Suicide 6, Earth was at 351 parts per million. When I started snowboarding at Pat's Peak, it had increased about 10 parts per million to 360 parts per million. When I started taking classes at University of New Hampshire as a student, the number I had to memorize for my exams was 380 parts per million. And today, now that I teach courses at UNH, I teach my students 450 parts per million. That was as of last semester. And when I teach again in the spring, I'm going to have to update this again because it keeps going up. When we look at the impacts on Earth's climate and what we're seeing more regionally, this is what we've seen in winter warming. Since 1970, the New England region in particular and the Midwest have seen much more winter warming. One thing you'll notice about this map is that there aren't any blue areas. That means there are no places in the United States that are seeing cooler temperatures in winter. Every place is warming, some regions much more than others. So when we think about winter climate warming, really we're talking about a contrast between climate versus weather. And I think Mark Twain said it pretty well. Climate is what you expect, and weather is what you get. Some years we do end up with those wonderfully snowy winters, and other years are kind of a bust. Like I remember 2015-16 in New England was quite the bust. That was a really tough year for everyone. Not much snow, really warm temperatures. But we can talk a little more scientific definitions. When you think about climate and weather, weather is the actual state of the atmosphere at a particular place in time. When you're talking about climate, however, Then we're thinking about a statistical description of weather over a much longer period of time, usually 30 years or more. So climate change is any change in that statistical description of weather over a longer period of time, and it has to be sustained. And we've seen that since the 1970s, our winters have gotten a lot warmer.